A single light year is nearly 10 trillion kilometers. The nearest star is more than 4 of them away. How far is that really, in anything a body can feel? It sounds simple. Light, 1 year, a very large distance. But it hides a second meaning it never admits. It also measures the past. Every star overhead is a different age. The whole sky 1,000 separate moments that only look like one. For most of history, we couldn't measure it at all. We still can't see most of it as it truly is. Tonight, we'll follow a beam of sunlight older than the first human cities. We'll meet stars that vanished before their light arrived, galaxies too old to exist, and light that will never reach us at all. And we'll end somewhere stranger than any of it, inside your own skull, where the present always runs a little late. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. Settle in. The light reaching your eyes is already old, and we're about to follow it home. Let's begin. Start with something close. The light reaching your eyes is old. Not ancient, not cosmic, just old enough to matter. Light is the fastest thing there is. Nothing in the universe outruns it. It moves about 300,000 kilometers every second. In that 1 second, it could circle the whole Earth 7 times. Snap your fingers. 7 laps around the planet, already done. There is a famous way to hold that speed in your hand. A computing pioneer named Grace Hopper used to give people a short piece of wire, a little under a foot long, and call it a nanosecond. Because that is how far light travels in a billionth of a second. That much wire per billionth of a tick. You could hold the universe's speed limit cut to the length of a forearm. So here on the ground, light is as good as instant. A lamp switches on, and the far wall brightens with no delay we could ever feel. We built our entire sense of now on that. Seeing and happening felt like the same thing. But leave the ground, and the delay begins. The moon is a little over 1 light second away. Glance at it, and you see it as it was a second ago. Small, easy to forget. The sun is farther. Its light takes about 8 minutes and 20 seconds to reach us. You'd expect to see the sun as it is. You never have. Not once. You see it as it was 8 minutes ago. Every morning, every sunset, your entire life. And it gets stranger. The warmth itself is older than that. Deep in the sun's core, light is born. But it cannot fly straight out. It is trapped in a crowd so dense that it can barely move before it slams into something and scatters. It bounces. It wanders. It claws its way toward the surface on a tangled, random path. That climb takes a long time. Not seconds, not years, something like tens of thousands of years. So the sunlight on your skin this afternoon carries energy that began its journey out of the sun's heart before the first human city was ever built. It surfaced, then it crossed to us in 8 calm minutes. Old twice over, old in the making, old in the crossing. And here is the quiet, unsettling part. If the sun simply stopped, went dark, vanished, we would not know. Not for 8 more minutes. The sky would stay bright. The afternoon would carry on. The Earth would keep curving along its orbit, held in place by a grip that hadn't heard the news yet. Because gravity is bound by the same limit. It carries no faster than light. For 8 full minutes, the whole world would live inside a sun that was already gone. The light and the pull would fail together, 8 minutes late, and only then would the planet drift free. Feel that. The now we trust does not reach the sky. It stops somewhere just past our own skin. It does not even reach your own hand. Hold it up in front of your face. The light bouncing off your skin takes a tiny sliver of time to cross the gap to your eyes, a fraction of a billionth of a second. Unmeasurable to you, but real. Even looking at yourself, you are looking very slightly into your own past. There is no exception anywhere. Not the hand, not the page, not the face across the table. Everything you have ever seen, you saw a little late. This is the rule, and it never bends. To see a thing is to see its past. The farther away it sits, the deeper the past you are looking into. Across a room, the delay is billionths of a second. Across the solar system, minutes. Across the galaxy, we will see much, much more. And this speed is not really about light at all. It is the speed of cause and effect itself. Nothing, no light, no signal, no push or pull of any kind can carry from one place to another any faster. When you clap your hands, the sound crawls to the far wall and back. Light does the same thing, just unimaginably quicker. But it is still a journey, still a delay, still a small piece of time spent crossing a small piece of space. We feel this more often than we know. The satellites that guide a phone to its location have to account for the time their signals take to fall to the ground. Get that timing wrong by even a fraction, and the map would place you streets away from where you stand. The delay is not a curiosity tucked away in the stars. It is woven into the most ordinary mornings, quietly corrected for, never noticed. And the conversations we have prove it without our noticing. Talk to someone on the far side of the world by satellite, and you can sometimes hear it, that small, awkward gap before they answer. That pause is not rudeness, and it is not the machinery being slow. It is the time their voice spent climbing up to a satellite and falling back down at the speed of light the whole way. Even a human conversation, stretched across the planet, runs on the delay. We have simply learned to talk around it. There is something the mind cannot quite do with all this. Light is the fastest thing that exists, and we have just called it slow. Both are true at the same instant. On a human scale, nothing is quicker. On a cosmic scale, it crawls. The brain wants a single answer, fast or slow, and the universe refuses to give one. That refusal is where the trouble starts. If light is this fast, and these delays are this small, how did anyone ever notice the delay at all? How do you catch the fastest thing in the universe running late? We did, by watching a moon arrive late for an appointment. For most of human history, we believed light was instant. A flash was a flash. Everywhere, all at once. Some of the greatest thinkers who ever lived insisted light had no speed at all, that it simply was the moment it left its source. The argument ran for centuries and went nowhere. Light seemed to wait for nothing, so it seemed to take no time. Then a Danish astronomer noticed a moon behaving oddly. His name was Ole Rømer. The year was 1676, and the moon was Io, circling the planet Jupiter. Io is reliable. It loops around Jupiter in about 42 hours, like a clock that never needs winding. It slips into the planet's shadow on a strict schedule. Rømer timed those eclipses night after night, expecting them to land right on cue. For a while, they did. And then they didn't. As the months passed, the eclipses began arriving late, minutes later than they should. Then, half a year on, they crept back to being early again. Nothing was wrong with Io. The moon kept perfect time. What was changing was the distance. When Earth on its own orbit swung away from Jupiter, the light from each eclipse had to cross a wider and wider gap to reach him. That took extra time. When Earth came back around toward Jupiter, the gap shrank, and the light arrived sooner. The moon was not running late. The light was simply traveling, and the travel could be timed. That was the moment light stopped being instant. It had a speed, enormous but finite. And if it was finite, then everything we see is delayed by exactly how far away it is. Rømer did not even nail the number himself. He explained the cause. Others took his timings and turned them into a velocity, and their first guess came out about a quarter too low, hampered by rough figures for the size of Earth's orbit. But the principle was exact. The sky runs on a delay, and the delay is the distance. Decades later, another astronomer found a second, completely independent fingerprint of light's finite speed, a slight tilt in the angle of starlight as the Earth moved along its orbit. Two different methods, the same answer. The case was closed. Now hold that thought, because it took another century and a half to do the reverse trick. Seeing the delay was one thing. Measuring how far away a star actually was, that was something else entirely. For thousands of years, nobody could do it. Not for a single star. We could name them, navigate by them, build calendars and gods around them. But we had no idea whether a given star was near enough to nearly touch or impossibly far. The sky had a depth we simply could not read. Then, in 1838, a German astronomer named Friedrich Bessel cracked it, and he chose a strange target, not the brightest star, a dim, unremarkable one called 61 Cygni. He chose it because it moved. Most stars seem frozen across a human lifetime. A few drift, very slightly, year over year. And a star that drifts quickly is usually a near one, the way a close streetlight slides past a moving car, while distant lights barely budge. 61 Cygni was one of the fastest movers known. An earlier astronomer had nicknamed it the Flying Star. So Bessel guessed it was close. Close was the only thing he had any hope of measuring. His method is one your own eyes perform constantly. Hold up a finger. Look at it with one eye, then the other. It jumps against the far wall. That jump is parallax, the shift of a near thing against a distant background when your viewpoint moves. Earth gave Bessel two enormous eyes, its place on one side of its orbit and its place 6 months later on the other side, nearly 300 million kilometers apart. He measured how much 61 Cygni shifted between those two viewpoints. The shift was almost nothing, a hair, the smallest angle anyone had ever pried out of the sky. But from that hair came a distance, about 11 light years, the first real distance to any star ever. After thousands of years of looking up, a human being could finally say how far one of those lights truly was. Less than 2 centuries ago, within the span of a few long lives, laid end to end. That single trick gave astronomy a unit it still uses today. Because the angle for the nearest stars is so absurdly tiny, distances got built straight out of it. The parsec, named for the parallax of 1 arc second. Every time the word is spoken, it is a quiet monument to Bessel's hair-thin angle. But parallax has a wall. The jump shrinks as you go farther out, until no instrument on Earth can catch it. To measure the deep sky, we needed another ruler. And it came, a few decades later, from a woman the field barely let through the door. Her name was Henrietta Leavitt, and she found the ruler in the blinking of stars. She was deaf. She worked at Harvard cataloging stars on glass photographic plates. for a fraction of an astronomer's wage and almost none of the credit. The job title they gave women like her was computer. She was studying stars that pulse, brightening and dimming on a cycle, and she noticed a pattern so clean you could set a clock by it. The brighter ones pulsed slowly. The dimmer ones pulsed fast. The rhythm of the blink told you the star's true brightness. That was the key. If you know how bright something truly is, and you measure how bright it merely looks, the gap between the two tells you how far away it must be. Leavitt had found a candle that announced its own flame, just by the speed of its flicker. Within a decade, Edwin Hubble used her ruler on a faint smudge called Andromeda. He measured it, and the answer was staggering. It was not a cloud inside our galaxy. It was another galaxy entirely. The known universe grew enormously, overnight, on the back of a pattern a deaf woman found while being paid merely to count. She died of cancer in 1921, before the field fully understood what she had handed it. A few years later, a mathematician began the process of nominating her for the Nobel Prize, not knowing she had already passed, and that the prize cannot be given to the dead. The recognition arrived too late to reach her. Some light takes too long to get where it was going. So we had learned light has a speed, and we had learned to measure the distance it crosses, which means we could finally ask the real question, the one this whole night turns on. What exactly is a light year? A light year sounds like a unit of time. It is not. It is a distance. It is the distance light travels in 1 year. Take that speed from before, 300,000 kilometers a second, 7 laps of the Earth between heartbeats. Now let it run, not for a second, for a whole year, every second of every day without stopping at that speed. The line it draws in that time is 1 light year, nearly 10 trillion kilometers. The number is too big to feel, so we break it into smaller steps. A light second reaches the moon. A light minute crosses much of the inner solar system. 8 light minutes to the sun. Light hours carry you out past the farthest planets. And a single light year is larger than all of that put together, many thousands of times over. The unit even fools us in ordinary life. Think of every story where someone says a journey was 12 light years long and means it took 12 years. It doesn't. A light year never measures time. It only ever measures space. And yet, it smuggles time inside itself anyway. Because to look across that space is to look into the past. So, translate 10 trillion kilometers into something a body can hold. If you shrank 1 light year down until light moved at the pace of a slow walk, crossing that single distance would still take you longer than all of recorded human history. That is 1, just 1. Now look at the nearest star, Proxima Centauri. You'd expect the closest star to be close. It is not. It sits more than 4 light years away. The light arriving from it tonight left a little over 4 years ago. So whatever Proxima is showing us, it is showing us a star as it was 4 years before this night. Picture your own life 4 years ago, who you were, what you worried about, what you hadn't yet learned. That is the moment frozen in the light, now landing in a telescope. The 2 ends of the same beam, only one of them has aged. And here's something humbling about our nearest neighbor. For nearly all of human history, we didn't even know it was there. Proxima is a red dwarf. Small, cool, so dim that no human eye can see it without a telescope. The closest star to our sun, the nearest thing in the entire universe outside our own solar system. And we did not discover it until 1915. We had cathedrals and symphonies and ocean-spanning empires long before we knew which star was nearest to home. It hides in plain sight. It belongs to a system of 3 stars, and the 2 bright ones there look like a single brilliant point to the naked eye. Proxima is the faint third member, drifting a little closer to us than the others. It took the better part of human history and a good telescope to notice it at all. Sit with that, the closest companion our sun has in all the dark. And we walked beneath it, unknowing, for thousands of years. Its 2 bright siblings are a matched pair, one much like our own sun, the other a little smaller and cooler, circling each other in a slow waltz that takes the better part of a century. 3 stars, bound together, the nearest family we have. And even reaching the closest of them is beyond anything we can do. The fastest probe we have ever launched would need tens of thousands of years to arrive. Engineers have sketched wilder ideas, tiny featherweight craft pushed by lasers, racing at a fraction of light speed, and even those dreams would take 20 years just to get there, and another 4 for the news to come home. 4 light years to the very nearest one, and it is the closest distance in this entire night. Everything from here gets larger. There is something quietly remarkable in that 4. It means the nearest stars sit within a single human lifetime of light travel. The light from Proxima arriving tonight is younger than a child starting school. The light from the next handful of stars is younger than most of the people reading this. So the closest sky is not ancient at all. It is a record of the recent past, the last few years and decades written in light. The deep antiquity comes later, farther out. Here, near home, the sky is almost current. Almost. And notice what the unit is really doing for us. 10 trillion kilometers is a number, but it is not a thought. The mind slides right off it, the way it slides off a billion or a trillion of anything. So we fold the whole crossing into 2 small words, a light year. Suddenly the unholdable has a handle. We can say it, we can put it in a sentence and carry it around. We cannot truly picture it, no one can, but we no longer have to. The unit was invented not to help us understand the distance, but to let us speak of it at all, to make the impossible at least sayable. That is its quiet kindness and its quiet trick. And of all the units we could have chosen, this one is strangely honest. A kilometer hides the truth. It pretends space is just space, a flat, empty room you could cross if only you were quick enough. But a light year carries its secret right there in the name. It admits that distance and time are the same fabric. It tells you, every time you say it, that to look across this gap is to look backward, that you cannot have the space without the years. We could have measured the heavens in cold, neutral numbers. Instead, we measure them in light and in time, which is the only way the heavens have ever actually spoken to us. The unit itself confesses what the universe is really made of. But a number on its own stays abstract. So let's stop measuring the distance from the outside. Let's go inside it. Let's leave home and travel out toward that star and feel how truly empty 4 light years are. Now, imagine you leave. You rise off the Earth and head outward toward Proxima at the speed of light itself. What do you find? At first, the familiar. The moon, gone in just over a second. Then the inner planets, falling behind one by one. The sun shrinking at your back. You cross the orbit of the farthest planet in a matter of hours. The entire bright family of worlds behind you before a single day is out. And then, nothing. for a very long time. This is the part the diagrams never show you. The solar system is not the planets. The planets are a tiny crowded clump near the center of something vastly larger. Keep going. You reach the place where the sun's wind of particles finally loses its push against the thin gas between the stars, a frontier called the heliopause. Light takes most of a day to get there. We have actually sent something across it, a spacecraft launched in 1977, now drifting in interstellar space, the most distant human-made object there is. It still whispers back to us, though its signal arrives so faint that the dishes on Earth catch a power smaller than a billionth of a watt. It carries a golden record bolted to its side. Greetings in dozens of languages, music, the call of a whale, the sound of a human heartbeat, a message in a bottle thrown into a sea so wide that the nearest far shore is tens of thousands of years away. We made it knowing almost no one will ever find it. We made it anyway, and even that lonely craft has barely begun. It is about 1 light day out. The journey you're on is more than 4 light years. Keep drifting. Eventually you reach the Oort cloud, a faint, enormous shell of icy bodies wrapping the sun like a sparse cocoon. It is the source of the long-period comets that occasionally fall inward and blaze across our skies. And it reaches outward an astonishing distance, perhaps 1 light year, perhaps closer to 2. Think about what that means. The outer edge of our own solar system may stretch nearly halfway to Proxima Centauri. Our system and the next stars may very nearly brush against each other in the dark, edge to edge, with almost no truly empty space between them. Anchor the scale because it is hard to believe. Shrink the distance from the Earth to the Sun down to a single step. On that scale, all the planets fit inside a small courtyard. The heliopause is down the block, and the far edge of the Oort cloud is several kilometers away. The bright, busy part we call the solar system is a single courtyard, at the center of a structure that spans a town, and almost all of that town is dark, cold, empty, lit by a sun that from out there looks like just another bright star among thousands. And what fills the dark between the courtyard and the next one? Almost nothing at all. Out in interstellar space, matter thins to a few stray atoms in a space the size of your fist. No air, no sound, no warmth, no landmarks of any kind. Just the slow, silent drift, with the sun behind you shrinking until it is only the brightest star in a sky full of them. And then, eventually, not even the brightest. If you stood out there and looked back, you could not pick out the Earth at all. Not the oceans, not the cities, not a single living thing. Only a faint point of light, lost in the glare of the sun, itself just one spark among thousands. Everything you have ever known, every person who has ever lived, folded into a dot you could hide behind a raised thumb. You were born in the courtyard. Nothing human has come anywhere near the far walls. Nothing will, for a very long time. Because here is the cruelty of it, felt as motion instead of math. That spacecraft, falling outward for almost 50 years at tens of thousands of kilometers an hour, would need more than 70,000 years to reach Proxima, if it were even aimed there. 70,000 years to the nearest star. Whole civilizations rise and fall in less. And suppose you arrived. Suppose you crossed all of it and reached Proxima at last. What would be waiting? A small, dim, sullen red star, far cooler than our sun, prone to violent flares, glowing the deep red of a dying ember. and circling it, a world roughly the size of Earth, sitting at just the right distance for liquid water. We have found it. We have named it. We will likely never touch it. It hangs there, 4 light-years off, a possible second shore that no human hand will ever reach, visited, if at all, only by the faint light we send and the faint light it sends back. A crossing like that would swallow generations. The travelers who set out would not be the travelers who arrived. The journey itself would become a kind of moving home, a small, warm world of its own, drifting through the long dark, carrying the children of whoever first dared to leave. And imagine the quiet of it. Out there between the stars, there is no day and no night. Only a black sky scattered with unblinking points of light that never rise and never set. The sun, by then, just one of them. No weather, no horizon, no sound at all, because there is almost nothing to carry it. For year after year after year, nothing would change in the view but the slow, almost imperceptible drift of the nearest stars. The distance is not only vast, it is patient and silent and indifferent to whether anything ever crosses it. That indifference is the truest face of the scale we are dealing with. And these are the close distances, the neighborly ones, the ones inside our own backyard. Because once we leave that backyard, once we cross from a single star to the whole vast city of stars we belong to, the numbers stop being merely large. They become something the mind cannot hold at all. We live inside the Milky Way, and we have never seen it. Not all of it, not as it is now. We live inside it, and that is exactly the problem. The galaxy is about 100,000 light-years across. Picture that. Light, the fastest thing there is, needs 100,000 years just to cross our home from one side to the other. We sit roughly halfway out from the center, tucked inside one of its spiral arms, looking outward through a haze of nearer stars and thick lanes of dust. You'd think we'd at least have a photograph of home. We don't. Not a real one. Every image you have ever seen of the full Milky Way, spread out like a glowing pinwheel, is one of two things. Either it's another galaxy standing in for ours, or it's an artist's reconstruction, stitched together from indirect clues. No camera has ever floated far enough out to take the actual portrait. And none ever will, not on any timescale that means anything to us. To get far enough away to fit our galaxy in the frame, a probe would have to travel for far longer than our entire species has existed. We don't even sit still inside it. The whole solar system is sweeping around the galactic center, dragging us with it at speeds that would carry you around the Earth in minutes. And yet the galaxy is so vast, at one full lap, one galactic year, takes something like 225 million years. The last time we were in this exact spot, dinosaurs had not yet appeared. At the very center where all those stars wheel around sits something we cannot see directly at all. A black hole millions of times heavier than the sun. We know it is there because we have watched stars whip around an invisible point, flung along tight, fast orbits by a gravity with nothing visible at its core. And the whole galaxy is not still either. The entire Milky Way, every star, every arm, the black hole at the center, us, is itself falling through space, drawn toward distant concentrations of mass far larger than anything nearby. We are moving at hundreds of kilometers every second, and have been for the whole of human history, and felt nothing. No wind, no motion. The ground beneath you seems perfectly still, and it is racing across the cosmos faster than any machine we have ever built. There is no standing still anywhere in the universe, only the illusion of it, granted by distances too large to feel ourselves crossing. But the deeper strangeness is the time folded into the size. When we look toward the far side of our own galaxy, that light has spent tens of thousands of years crossing to reach us. So we see the opposite edge of home as it was when the last ice age still gripped the planet, when humans were painting on cave walls. The near side and the far side do not show us the same moment. Our own galaxy is not a single now, it is a smear, 50,000 years and more, all arriving at once, and we sit somewhere inside the smear, looking out. Anchor it with a city. Imagine trying to photograph the place you live, except the far neighborhoods only show you scenes from thousands of years ago. The middle distance shows you centuries past, and the only viewpoint you will ever have is your own front step. That is our relationship to the galaxy, intimate and blind at the same time. We are actually more certain of the shape of galaxies millions of light years away, seen cleanly from outside, than we are of the shape of the one we have never left. We are filling in the map by other means. A spacecraft built to measure the precise positions of more than 1 billion stars has been quietly redrawing the Milky Way from the inside, and it found surprises. Our galaxy's disk is not a flat, tidy plate. It is warped, rippling, as though something passed through it long ago and set it gently ringing, like a struck bell. We are learning the shape of home the way someone blind from birth learns a room. By touch, by inference, by patient mapping, never by simply looking. And consider how little of it we actually see. Every single star you can pick out on the darkest night, every one your eyes have ever caught, sits within a tiny bubble of our own spiral arm, a few thousand light years across, at most. A small, well-lit room in a house with 100,000 light years of hallways. The other hundreds of billions of stars in the Milky Way are simply too far and too faint, hidden behind dust, blurred into the soft band of light that gave our galaxy its name. When our ancestors looked up and saw a river of milk spilled across the sky, they were seeing the combined glow of countless stars too distant to separate. The rest of our own home smeared into a haze, 100,000 light years across, and the far side is still showing us the Ice Age. Even the center is deep in the past. The heart of the galaxy, where that great black hole sits among a fierce crowd of stars, lies around 26,000 light years away. So the glow we gather from the galactic core left it before the last Ice Age ended, before farming, before writing, before the first stone was set on a stone. We are watching the center of our own home as it was when our ancestors were still hunting mammoths. The Milky Way does not show us a single moment anywhere. Every direction we look into a different depth of time. Now hold one more thought before we go further out. If the light from a distant star takes that long to arrive, then the star itself has all that time to change, to age, to end, which means some of the lights we steer by may not be there anymore. Now step outside on a clear, dark, moonless night, away from the city. Let your eyes adjust to the dark, slowly, the way they were meant to. Look toward the constellation Andromeda, and find the faint smudge there, a small, dim oval of light, easy to miss. What are you actually looking at? You are looking at another galaxy, the Andromeda Galaxy, and it is about 2.5 million light years away. The light landing in your eyes right now left it around 2.5 million years ago. Hold that against the human story. 2.5 million years ago, there were no people. Our ancestors walked upright on the African savanna, shaping the first crude stone tools, with brains a fraction of the size of ours. The light now reaching you set out before our kind had fully become itself. It crossed the dark for the entire length of human existence, and then some, and finished its journey just now, in the back of your eye. And this is not one star running late. This is 1 trillion stars, every one of them sending light from 2.5 million years in the past, all arriving together as one soft glow. So, you are not watching Andromeda. You are watching a portrait it painted of itself long ago, addressed to no one, that happened to find an eye at the far end of its delivery. Feel what your body is doing right now. No telescope, no instrument, just the eyes you were born with, and they are catching light 2.5 million years old. That faint smudge is the oldest light and the farthest distance the unaided human body can ever reach. There is nothing more distant you can see without a machine. Stand under it, and you are personally receiving a signal that predates your entire species. It is worth remembering how recently we understood what it even was. Only about 100 years ago, the smudge was thought to be a small cloud of gas inside our own galaxy. Then Hubble measured it with Leavitt's blinking stars, and the cozy little universe we thought we lived in cracked open into something vastly, dizzyingly larger. But there is a twist in Andromeda's story, one almost no other galaxy shares. Nearly every distant galaxy is racing away from us. Their light arrives stretched and reddened by the fleeing. Andromeda is not. Andromeda is approaching. Its light reaches us slightly compressed, shifted toward the blue, the signature of something falling closer, not drifting away. We are bound to it by gravity, and the two galaxies are drawing together, closing the gap at something like 100 kilometers every second. In roughly 4 to 5 billion years, the Milky Way and Andromeda will meet, slowly, gently, by our standards. Their stars are so far apart that almost none will actually collide. The two great spirals will pass through each other, tear at each other's shape, swing back, and over hundreds of millions of years, settle into a single new galaxy. So, the ancient glow you receive is not a farewell. It is the early light of a long approach, a neighbor that has been quietly coming toward us since before we had eyes, and will still be arriving long after we are gone. And there is a strange beauty waiting in that approach. Right now, Andromeda is a faint smudge, small enough to cover with a fingertip, but it is growing. Slowly, across millions of years, it will swell in our sky, brightening, spreading, until one distant night it would stretch across the heavens, far wider than the moon. A vast spiral of light no human alive today will ever see. We catch it at the very beginning of its arrival. A whole galaxy drawing near, one quiet century at a time. Andromeda is also the giant of our little neighborhood. Our galaxy belongs to a small cluster, the local group, of a few dozen galaxies bound loosely together. Most are tiny, faint dwarfs. Only a handful are grand spirals, and Andromeda is the largest of them all. This is our corner, our family of galaxies, falling slowly together against the expansion that is carrying everything else away. 2.5 million years, and it is one of the closest things in the deep sky, and it is not even the farthest your bare eyes can reach. Under a truly black sky, far from any human light, with patience and a little luck, some people can just make out a second, even fainter smudge, the Triangulum Galaxy, another spiral, farther still, near 3 million light-years away. To see it at all is to push the human eye to the very limit of what it can do. Beyond that, the body simply cannot go. Every galaxy more distant than these few requires a machine. We are nearly blind out here, and the little we can see unaided is already millions of years old. Stay with the merger for one moment more, because of what it tells us about looking. When the Milky Way and Andromeda finally fold together, there will be no one alive who remembers tonight. The sun will be old and swollen. Earth, if it survives at all, will be unrecognizable. And the night sky of that distant world will blaze with the tangled light of two galaxies becoming one. Yet that light, too, will be old by the time it is seen. Every bright lane of it, a memory in transit. There is no era, no vantage, no future eye anywhere that ever gets to see the universe as it truly is in the same instant. The delay is not a problem we will one day solve. It is simply how seeing works, forever, for everyone. Now lower your eyes from Andromeda and think about the ordinary stars overhead, the familiar ones, the ones in the shapes you know. Because if light can outlast its journey, it can outlast its source. And some of those stars may already be gone. Some of the points of light in tonight's sky no longer exist. The light is still arriving. The star itself is gone. This is the quiet consequence of everything so far. If a star is far enough away, its light can take longer to reach us than the star lasts in the form we are seeing. The light outlives the source. We keep receiving a signal from something that has already changed beyond recognition, collapsed, or torn itself apart, and we will keep receiving it faithfully for as long as the old light keeps streaming in. Now be honest about the scale of this, because the idea gets exaggerated. You'd expect half the night sky to be a graveyard. It isn't. Most of the stars you can see with the naked eye are relatively close, within a few hundred or a couple of thousand light years, and most of them are stable, middle-aged stars that are almost certainly still shining right now, tonight, as you look at them. The dramatic version where the sky is full of ghosts is not true. The quiet truth is stranger because it is uncertain. For some of them, we simply cannot say. We will not know until the light finishes arriving. Take Betelgeuse, the red shoulder of the constellation Orion, a swollen, dying giant, somewhere around 500 to 600 light-years away. It is near the end of its life. Someday it will explode as a supernova, a single star, for a few weeks outshining the entire galaxy around it, bright enough to be seen in daylight. In late 2019, it did something that made headlines around the world. It dimmed, dramatically, more than it ever had in modern records. For a few months, people wondered, half seriously, whether they were watching the beginning of the end, whether the explosion had already happened centuries ago, and the news was finally arriving. It turned out to be dust. A vast cloud the star had belched out, dimming it for a season. Betelgeuse brightened again, but the question it raised was real. Because when astronomers say Betelgeuse could go any time, they mean any time in the next 100,000 years. And there is a genuine, if small, chance that it has already exploded, that the blast happened centuries ago, and the light of it is still crossing those last hundreds of light years toward a sky that for now still shows the star calmly burning. We don't know. That is the honest answer, and there is no way around it. We cannot know until the light gets here. We have at least seen this happen once in modern times. In 1987, light reached Earth from a star that had exploded in a small neighboring galaxy, about 168,000 years ago. We called it a supernova and watched it brighten in our southern sky. But the light was not the first thing to arrive. A few hours before it, our detectors caught a faint shower of ghostly particles called neutrinos, flung out of the dying star's collapsing core, racing across 168,000 years of space and reaching us first. We didn't just see a star die. We felt the breath of its collapse arrive ahead of its glow. So the truth about a star is always somewhere in the dark, in transit, traveling at the only speed truth can travel. And we are downstream of it, waiting, with no way to hurry the message along. Sometimes the death is still hanging there, visible centuries later. On a quiet night in the year 1054, astronomers in China and across the world recorded a guest star, a new light that flared so bright it could be seen in daytime for weeks, then slowly faded. They did not know what they were watching. We do now. It was a star tearing itself apart, about 6,500 light years away. The explosion had actually happened 65 centuries before they saw it. Its light had simply only then arrived. And today, if you point a telescope at that same spot, you find a glowing, tangled cloud of debris still flying outward, the shredded remains of the star they saw die 1,000 years ago. The death and its aftermath both delivered to us late, on a long delay. It is a strange thing to hold, to look up at a familiar star and not be able to say, even in principle, whether it still exists. So we carry that small uncertainty into the dark, not as fear, just as the texture of living inside a delay. And some stars leave behind something that keeps signaling long after the death. When the largest stars collapse, what remains can be a tiny, impossibly dense core. A city-sized ball heavier than the sun, spinning many times a second, firing beams of radiation out into space like a lighthouse. Each time a beam sweeps across the Earth, our instruments catch a pulse. Tick, 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 so steady you could set a clock by it. We are receiving the rhythmic heartbeat of a star that already died, the body gone, the corpse still spinning, still calling out across the light years with mindless, perfect regularity. And there is one more thing these dying stars are quietly showing us: our own future. Our sun is a star like the others. It too will run down. In several billion years, it will swell, redden, and shed its outer layers, leaving behind a slowly cooling ember. So when we study a distant star in its final act, its light hundreds or thousands of years old, we are not only looking across space and back in time, we are looking ahead at a fate our own sun shares. The sky is full of beginnings and endings, all arriving at once, all on delay. And somewhere among them is a preview of how our own light will someday go out. And if a single dying star can hide its fate behind a few hundred light years, imagine what hides behind billions. Imagine pointing our finest eye not at a bright star at all, but at the emptiest, blackest, most nothing scrap of sky we could find. That is exactly what we did. And what came back rewrote the size of everything. In 1995, astronomers did something that sounded reckless. They aimed the Hubble Space Telescope at a patch of sky so small and so apparently empty that pointing one of the most valuable instruments ever built at it seemed close to a waste. A speck near the handle of the Big Dipper, about the size of a grain of sand, held at arm's length. As far as anyone could tell, it contained nothing. No bright stars, no known galaxies, just black. The decision fell to one person, the observatory's director, who held a reserve of telescope time to spend at his own discretion. Pointing it at apparent nothingness for days on end was a real gamble with his reputation. If the image came back empty, he would have burned a fortune of irreplaceable observing time on a blank square of dark. Plenty of respected voices thought it was a mistake. He did it anyway. They left the shutter open for 10 days, and what came back rewrote the sense of scale for everyone who saw it. That tiny black speck was not empty. You'd expect a few faint dots at most. Instead, it held around 3,000 galaxies. Not stars, galaxies. Each one a city of 100 billion suns, stacked into the dark, growing fainter and smaller and redder the deeper the image looked. Later versions of the experiment, looking longer and reaching deeper, pulled 10,000 galaxies out of a fragment of sky a person would have sworn was blank. And because looking far is looking back, the faintest of those galaxies were also the oldest. Their light had traveled for billions of years, showing them as they were when the universe was young. A single grain of sand patch of nothing turned out to be a core sample, drilled straight down through cosmic time. The recent universe near the top of the frame, the infant universe at the very bottom. Then, decades later, a new eye opened. The James Webb Space Telescope. It sees in infrared, which lets it catch light so ancient and so stretched by the expanding universe that the older telescopes missed it entirely. Its very first deep image, released in 2022, showed thousands of galaxies in a patch of sky you could cover with a grain of sand at arm's length. And it reached farther back than anything before it. Some of those galaxies are seen as they were more than 13 billion years ago, within a few 100 million years of the beginning of everything. And here is where it stopped being a victory lap and became a genuine mystery. We expected the earliest galaxies to be small, faint, ragged, just beginning to come together. That is what the models predicted should be there. Half-formed things struggling into existence. Instead, Webb found some early galaxies that were too big, too bright, too mature. Well-formed systems, already crowded with stars, existing at a time when there should barely have been enough cosmic history for them to assemble. Some scientists, only half-joking, called them impossible. Nobody yet knows the answer. Maybe the early universe built stars far faster than we thought. Maybe we're misjudging the masses or the distances. Maybe the models need to be rebuilt. The debate is alive right now in journals, unresolved. We pointed a new eye at the actual evidence, and the evidence declined to match the picture we'd drawn. To reach that far, the telescope even borrows gravity as a lens. Place a massive cluster of galaxies between us and the deep beyond, and its gravity bends the light passing around it, magnifying and smearing the faint, distant galaxies behind it into bright arcs, the way a glass of water bends the world seen through it. We are using whole clusters of galaxies as a magnifying lens to glimpse things that would otherwise be far too faint to find. The universe, it turns out, comes with its own telescopes built into the fabric of space, if you know where to stand. And scattered through those early images are little points of intense red light that nobody fully understands yet. Too small, too bright, too strange to easily explain. We have given them a plain nickname and a great deal of argument. The map of the early universe is being redrawn faster than the ink can dry. Now here is the part that resets the mind gently and completely. There was nothing special about those patches. They were chosen precisely for being ordinary, for looking empty. Point the telescope at almost any equally blank speck in any direction at all, and roughly the same thing comes back. Thousands of galaxies in every grain of dark sky, everywhere. The emptiness was never empty. It was simply too far and too faint for us to have noticed, until we held still and let the old light gather. So the next clear night, look at the black between the stars, the part that seems like pure absence. That black is not absence. It is full. Every dark gap up there, down to the smallest, holds thousands of distant galaxies, their light too faint and too ancient for the eye, pouring toward us all the same. And yet there is a true darkness back there, hidden in the deepest part of the image, a time before any of these galaxies existed. After the first light of the early universe faded, before the first stars switched on, the cosmos passed through a long stretch with no shining things in it at all. No stars, no galaxies, just dark, cooling gas drifting in the black, waiting. We call it the Cosmic Dark Ages. It lasted a few 100 million years, and no telescope has ever seen straight into the heart of it, because there was nothing there to give off light. That is part of what these great new eyes are hunting, the very first dawn, the moment the first stars ignited and broke the darkness, somewhere out at the edge of time. We are reaching back, light year by light year, toward the instant the universe first switched on. We have not quite touched it yet, but all of this raises a question that sounds simple and turns out to be one of the strangest in physics. If that light has been traveling for 13 billion years, how far away is the thing that sent it? The obvious answer is wrong, and the real answer breaks the light year in half. The obvious answer is simple. The light traveled for 13 billion years, so its source must be 13 billion light years away. Clean, simple, and false. The universe is expanding, and not the way you'd picture it, not galaxies flying apart through space, like debris from an explosion. It is the space between them that swells. Picture dots inked onto the surface of a balloon as it slowly inflates. No dot moves across the rubber, yet every dot drifts away from every other, carried apart by the growth of the surface itself. The galaxies are the dots, space is the rubber. So, while that ancient light was crossing toward us for billions of years, the space it had already traveled kept stretching out behind it. And the galaxy that sent it kept being carried farther away the whole time. The galaxy whose infant light we now receive is not 13 billion light years away today. It has been swept much, much farther out. The most distant light that has had time to reach us comes from material that now sits something like 46 billion light years away, in every direction we look. That gives the observable universe a width of around 93 billion light years, even though only about 14 billion years have passed since the beginning. Sit with that contradiction. A cosmos wider than its own age, measured in light years. It should sound flatly impossible. Nothing travels faster than light, so how can things be farther apart than light could possibly have crossed in all of time? The resolution is subtle and complete. Nothing is moving faster than light through space. Space itself is the thing expanding, and expansion obeys no speed limit. The rubber can stretch as fast as it likes. Only things moving across it are bound by the rule. And here is the humbling edge of it. That 93 billion light-year span is not the size of the universe. It is only the size of the part we can see, the distance light has had time to cross since the beginning. Beyond that horizon, the universe almost certainly continues, possibly forever, full of galaxies whose light has simply never had time to reach us, and never will. We live at the center of our own little bubble of visibility. We call it the observable universe, not because it is all there is, but because it is all we can ever be shown. There is an oldest light, too, the deepest the eye can reach, not from a star, but from the universe itself, when it was only a few 100,000 years old. A moment when the whole cosmos cooled just enough for light to travel freely for the first time. That first light is still arriving from every direction at once, stretched by all those billions of years into a faint hum of microwaves. We found it by accident. In the 1960s, 2 engineers kept hearing a faint hiss in a radio antenna and couldn't get rid of it. They checked the wiring. They cooled the equipment. They even cleared out the pigeons roosting inside and scrubbed away the droppings. Sure, the mess was to blame. The hiss stayed. It came from everywhere, day and night. They had stumbled onto the afterglow of the beginning of the universe. And at first, they thought it was bird mess. It is the edge of what can ever be seen. Beyond it, there is no older light to find, because before it, light could not travel at all. And this is where the light year starts to come apart in our hands. It was built on a simple promise that a distance and a travel time were 2 names for one thing. Expansion quietly broke that promise, so a single distant galaxy does not have one distance. It has 3. The distance it was when it released the light, close because the universe was small then. The distance the light actually traveled, the long stretching road. And the distance the galaxy sits at right now, the largest by far. All 3 are true. All describe the same galaxy. And they disagree by tens of billions of light years. We never even measure those distances directly. We can't lay a ruler across the void. What we measure is color, how much the galaxy's light has been stretched and reddened by the journey. From that single reddening and a model of how the universe has grown, we calculate everything else. How do we read the stretch so precisely? Each chemical element leaves a sharp, unmistakable fingerprint in light, a fixed pattern of bright and dark lines, always in the same places. Hydrogen here, oxygen there. We know exactly where those lines should sit. So when the light of a distant galaxy arrives with its whole fingerprint shifted toward the red, we can measure the shift down to a fine edge, because we know precisely how far each line has slid from where it began. The galaxy is not just glowing. It is carrying a coded message about how much space has stretched since the light left. And we have learned to read it. The distance is a story we reconstruct. The redness is the only thing the universe actually hands us. And even the story we reconstruct has a crack running through it. We have 2 excellent independent ways to measure how fast the universe is expanding, and so how big and how old it is. One works outward from nearby space, climbing a ladder of measurements, star by star, exploding star by exploding star, into the deep. The other works from that oldest light, the afterglow of the beginning, using our best physics to predict how fast everything should be expanding now. The 2 methods should agree. The gap between them is small, but it has refused to close. As the measurements have grown sharper, the disagreement has grown sharper too, harder to wave away as a simple mistake. something is wrong, and nobody yet knows what. Maybe a flaw hides in one method. Maybe there is something in the early universe we don't understand. After everything we have measured, our two best rulers for the cosmos still quietly contradict each other. The ruler is unfinished. The map has a seam we can see and cannot yet repair. And one of those three distances carries the heaviest weight of all. Because if the gap between us and a galaxy is still growing fast enough, then its light may never finish the trip at all. There are galaxies in the universe whose light will never reach us. Not yet. Never. They are shining right now. They are sending their light straight toward us, and we will never receive it. The road between us is lengthening faster than the light can travel down it. This is the consequence of an expansion that does not merely continue, but accelerates. The more distant a galaxy is, the faster the space between us and it stretches. Beyond a certain distance, that stretching outpaces light itself. A beam leaves such a galaxy, aims straight at us, moving at the fastest speed there is, and the gap ahead of it grows faster than it can close. The light runs forever and never arrives. Feel it through something a body knows. Imagine trying to walk up a slope that is sliding downhill beneath you, faster than you can climb. You move with everything you have. You never rise. The ground gives way exactly as fast as you gain it. There is a boundary to this. It has a name, the cosmic event horizon, and it is closer than you'd think. Galaxies only a moderate distance beyond what we can comfortably see are already, in effect, lost to us forever. Inside that boundary, light still has a chance of reaching us someday. Beyond it, the connection is already permanently severed. And here is the part that stills the breath. Galaxies we can see tonight, whose ancient light we are still receiving, are crossing that boundary as the expansion speeds up. The last light they will ever send our way is already on its way. Everything they emit after it will never come. We are watching, in unimaginably slow motion, the universe close around us. Not violently, not soon, over spans of time that dwarf the lifetimes of stars, but the direction is set, and it does not reverse. And follow that to its end. Cosmologists have, far enough into the future, the accelerating expansion will carry every galaxy outside our own gravitationally bound neighborhood beyond that horizon. The distant galaxies will slip away, their light stretched into nothing, the rest of the universe gone dark and silent. Astronomers living in that far future, looking out with the finest instruments imaginable, would see only their own island of stars, surrounded by perfect, featureless black. They would have no way of knowing the wider universe had ever existed. The expansion, the other galaxies, the whole grand structure we are uncovering right now, all of it erased from their sky. The evidence itself carried away, which means something quietly precious about this exact moment. We live early enough to still see it, to still catch the light of distant galaxies before the dark closes over them, to still read the story of expansion written plainly across the sky. We are not living in the universe's empty old age. We are living while the lights are still on, and that is not nothing to be grateful for. Think of it as a window that is slowly closing. Right now it is wide open, and the view is impossibly rich. Galaxies in every direction, the afterglow of the beginning still reaching us, the whole history of the cosmos pouring in. But the expansion is drawing the curtains, one distant galaxy at a time, far too slowly for any human to notice. Trillions of years from now, the view will be nearly bare. Anyone looking out then will see almost nothing, and will be able to deduce almost nothing. We happen to have arrived while there is still everything to see. Of all the eras the universe will pass through, we opened our eyes in one of the few when its full story is still legible in the sky. That timing is its own kind of grace. And it is not only light that obeys this limit. Gravity does too. We proved it recently in the most spectacular way. In 2017, two neutron stars, the collapsed cores of dead stars, each heavier than the sun, but squeezed into the size of a city, spiraled into each other in a galaxy about 130 million light-years away. The crash shook the fabric of space itself, sending out a ripple called a gravitational wave. And it sent out light. Both crossed 130 million years of space toward Earth. They arrived within about 2 seconds of each other. 2 seconds out of 130 million years. That is not coincidence. It is proof, written across the visible universe, that gravity travels at exactly the speed of light. The same delay governs them both. The same cosmic speed limit binds every kind of influence there is. That collision did one more thing worth carrying into sleep. In its heat, it forged heavy elements, including gold. Real gold scattered into space by the crash of two dead stars. Some of the gold on Earth, perhaps in a ring on someone's hand, was born in exactly such a collision, long ago and far away, and arrived here on a journey of unthinkable distance. So there is no shortcut, no signal, no influence, nothing at all crosses space faster than this one speed, which means there is no shared now. None. The present moment you live in does not stretch across the universe as one instant. It cannot. It is even stranger than a simple delay. Two people walking past each other on a street in opposite directions will not agree on what is happening right now in a distant galaxy. For one of them, a particular event out there lies in the future. For the other, at that very same instant of passing, it already lies in the past. Same street, same moment. Two different nows reaching out into the cosmos. This is not an error or an illusion. It is how time and space are actually stitched together. Every point in the universe has its own present, sealed off from every other by the speed of light. The cosmos is not one ticking clock. It is countless separate moments, each one local, each one unable to fully reach any other. That is the strangest thing the distance does. It does not just separate us in space, it dissolves the very idea of a single shared present. And after a truth that large, there is only one question left worth asking. Not how far, not how old, but what all of it means, for us, small and awake, looking up. So is the distance a tragedy? It would be easy to read it that way. And there is a hard, practical case for it. We can never go there. Not really. The nearest star is 70,000 years away, at the best speed we have ever reached. The galaxies are forever beyond any ship we could ever build. The far ones are slipping out of contact entirely, taking their light with them. We are sealed inside a small bubble of a vast and indifferent cosmos. We will never touch almost any of it. We will never stand beneath another sun, feel the warmth of another star, walk the surface of a world circling Andromeda. By every measure that matters to a body, the universe is a place we are locked out of, and in time, the doors only close further. That is one side. And it is honest. It deserves to be said plainly, without rushing to comfort. But here is the other side, and it is just as true. We may never cross the distance, but the distance crosses to us. The light comes, every single night, for free it arrives, from stars, from galaxies, from the very edge of time. We do not have to travel 2.5 million years to see Andromeda. We only have to step outside and look up and let it land in the back of an eye. The same delay that locks us out also delivers the entire history of the universe to our doorstep. Every photon is a messenger that has traveled, sometimes for billions of years, to reach exactly here, to reach us. The cosmos is not silent. It is constantly, patiently speaking, in light that left long before we were here to listen, and consider what it took to receive it. The universe spent nearly 14 billion years building atoms and stars and worlds, and finally, on at least one of them, a creature with eyes that could catch ancient light, and a mind that could ask where it came from. The distance did not only separate us from the cosmos, it is the reason we can see it at all. If light were instant, there would be no past written in the sky, no record, no depth. We would see only a flat, eternal now, and learn almost nothing. It is the delay that turns the sky into a memory, the distance that turns the universe into something we can read, layer by layer, all the way back to its first light. And there is one last turn, the strangest comfort of all. That delay does not stop at the edge of the sky. It lives inside you. The light from across the room reaches your eyes in an instant. But then, it has to become something you see. The signal travels up the nerve, into the brain, and gets assembled into an image. And that takes time. Tens of milliseconds. A touch on your foot reaches your brain later than a touch on your face, because the signal has farther to climb. Your brain gathers all these late arrivals, holds them, and stitches them into one smooth, seamless moment that feels perfectly present. But it never is. By the time you are aware of this moment, the moment has already passed. You live always a fraction of a second behind the world. So the trick the universe plays across billions of light years, your own mind plays across a few centimeters of nerve. The same delay, the same impossibility of touching the present cleanly. You are not separate from the strange thing the cosmos does with time and distance. You are made of it. There are careful experiments that catch the brain in the act. Show people a moving object and a brief flash side by side, and the mind nudges the moving one slightly ahead of where it truly is. A tiny error of timing that reveals the machinery underneath. The brain is not showing you the present. It is making a constant, educated guess about where the present probably is, and handing you the guess as though it were the thing itself. You have never once experienced now. Only the brain's best reconstruction of a moment already gone. And there is the harder truth on the skeptic side too, the one we shouldn't hurry past. Far enough into the future, the universe runs down. The stars burn out. The galaxies drift beyond reach. Everything cools toward a long, even dark. On a long enough timeline, the lights do go out and stay out. The window we are looking through is open only for a while. But a while here means many billions of years. And we are here now, in the open window, in the lit room, with the light still pouring in. That is not a small thing to be handed. It may be the rarest thing there is. And here is the part worth keeping. For nearly all of its history, the universe expanded and cooled and built its galaxies in total silence, with nothing in it to notice. No eye, no question. Light crossed unthinkable distances and landed on nothing that cared. Then, on at least one small world, matter arranged itself into something that could look up and catch that light and ask what it was and where it had come from and how far. That asking is the rarest thing we know of. Not the stars, not the distance, the wondering. The cosmos is full of light and almost empty of anyone to receive it. Tonight in this small room, you are the receiver. The universe spent billions of years and unspeakable distances arranging for someone to be curious about it. And here you are, being exactly that. The distance did not defeat us. It gave us something to wonder at, and the eyes to do it with. We don't resolve the wall and the window. We don't have to. The loneliness and the wonder are both true at once, and the night is large enough to hold them. So when your eyes feel heavy, let them close. The light will keep arriving whether you watch it or not. It always has. So the next time you step outside and look up, remember what you are really seeing. Not the sky as it is, the sky as it was. 1,000 different pasts layered into one quiet ceiling. Sunlight older than cities, starlight older than your species, galaxies that may already be gone. The distances are almost unbearable. 10 trillion kilometers to the nearest star, 46 billion light years to the edge of sight. Against numbers like these, we are unspeakably small. A single warm body on a single small world, awake for a single short while. But we are here, awake, conscious, looking up. And of everything that vast distance carries toward us, all that ancient light, crossing all that dark, we are the part of the universe that finally catches it and wonders. The cosmos spent nearly 14 billion years and almost unimaginable space to make something that could look back and understand even a little of it. That understanding is yours now. Carry it gently down into sleep. Sleep well under the light of stars that left long ago, and may you never see the night sky the same way again. The universe will still be here when you wake up. So will we. Good night.